Welcome! In this video, we're going to review the Kalman filter, which is one of the most commonly applied filters in multiple object tracking. We're going to talk about the prediction and the update, and we're also going to study an example of what happens in the prediction and in the update. Let's start by considering Bayesian filtering with the Chapman-Kolmogorov prediction and the Bayes update again. This recursion does not have a closed-form solution in general. However, there's an important exception to this general rule, a special case. And that is when the models that we use are linear and have additive Gaussian noise, and the initial prior is also Gaussian. In this case, a closed-form solution to Bayesian filtering is given by the Kalman filter. In fact, if all the noise is Gaussian and the models are linear, the Kalman filter is the so-called MMSE estimator, or the minimum mean squared error estimator. Before we review the update and the prediction in the Kalman filter, let's first review the basic models that are used. We have a Gaussian transition density that has a motion model F and a process noise covariance Q. We have a measurement likelihood that is also Gaussian with a measurement model H and a measurement covariance R. And in the Kalman filter, the initial density is Gaussian with mean vector x bar and covariance P. And the posterior density then, at time k, given measurements up to and including time tau, is Gaussian with mean vector x bar and covariance P. And the subscript indices here are used to denote that these are the mean vector and the covariance at time k, given measurements up to and including time tau. Now, let's have a look at the Kalman filter, the prediction, the updates, and the likelihood. In the prediction, we use the motion model F to predict the mean value, and the motion model also reshapes the covariance matrix, and process noise covariance Q is added, meaning that the uncertainty is increased. In the update, we start by computing a predicted measurement Z bar using the measurement model H. Using this predicted measurement, we can compute an innovation, here denoted epsilon. It's called innovation because it describes the new information in the measurement Z that was not captured in the predicted measurement. We use the measurement model H and the measurement noise covariance R to compute an innovation covariance S, and the innovation covariance is then used to compute the Kalman gain K. The updated mean vector is a weighted average of the predicted mean vector and the innovation times the Kalman gain. And the updated covariance matrix decreases the uncertainty. The uncertainty decreases because we are gaining new information from the measurement. And lastly, the predicted likelihood is a Gaussian PDF evaluated at the measurement Z with a mean value given by the predicted measurement and the covariance given by the innovation covariance. So the Kalman filter assumes linear models with Gaussian noise. However, in multiple object tracking, it is quite common that the motion model or the measurement model or both of them have to be nonlinear. In this case, it's possible to use nonlinear Kalman filters instead. For example, the extended Kalman filter, which is based on the linearization of the nonlinear models, or so-called sigma point Kalman filters, such as the uncentered Kalman filter or the cubature Kalman filter. The sigma point filters build on sampling. And if the models are highly nonlinear, or if we have very complicated noise processes, then nonlinear Kalman filter might not be sufficient. If that is the case, we can instead use particle filters. However, in many tracking applications, either the Kalman filter or one of its nonlinear variants is sufficient. So let's illustrate the Kalman filter with an example. So we have a scenario where we have a state with two states. We have position and velocity. This means that the state vector x has two elements. The first is the position, the second is velocity. We use a constant velocity model with sampling time t equal to 1. And the motion model is given by this matrix here. The process noise has mean value 0 and variance 0.5. The measurement model is a linear model that measures the position with some noise that has mean value 0 and variance 1. And let's also assume that we have an initial density that is Gaussian. It has a mean vector with position 1 and velocity 2, and a position variance of 0.3 and a velocity variance of 1. So we can visualize the initial density and one cycle of prediction and update of the Kalman filter. Here we have the mean position equal to 1 and velocity equal to 2. So the ellipsis shown is 2 standard deviations for the covariance matrix. And on the left and below, you can also see the marginal densities for the position and the velocity. In the prediction step, we used the motion model to predict the mean. We had an initial position of 1 meter and an initial velocity value of 2 meters per second. So the sampling time is 1 second, and that means that the predicted position is 1 meter plus 1 second times the velocity, which is 2 meters per second. And therefore, we get a predicted position equal to 3 meters. Since we're using a constant velocity motion model, the predicted velocity remains the same. So the predicted velocity mean is, of course, 2 meters per second. You can also see that the prediction covariance matrix has grown in size. The position and the velocity are more uncertain than they were before. This is because the motion model includes a process noise, and therefore it adds uncertainty. Another important thing that we can see from the covariance ellipse is that it is skewed. This is due to the fact that the prediction introduces a correlation between the position and the velocity. We know that the position is directly affected by the velocity in the prediction, and this shows up in the covariance matrix as a positive correlation. At time 1, we measure the position. So suppose that we get a measurement value of 6, here represented by the black line in the figure. After we have used this measurement in the Kalman update, we get this updated density shown by the dotted figure. We predicted the position to be 3 meters, and then we measured it with noise to a value of 6 meters. The updated position value should then fall somewhere in between these two values. And in this example, the updated position is about 4.75. We can also see that we have updated the velocity. It's no longer equal to 2. Instead, it has been updated to a value of about 3.5. So, despite the fact that we only measure position and not velocity, we still get an update of the velocity, because in the prediction we use the motion model, which in turn introduces a correlation between the two states, a correlation between the position and the velocity. In the prediction, the motion model leads to a predicted velocity value of 2. However, the position measurement value is 6, which suggests that we are actually moving faster than what we had predicted. So in this case, we get an updated velocity of about 3.5. And for the updated covariance, we can see that it is smaller than the predicted covariance. We are much less uncertain about the position and the velocity. And this holds especially true for the updated position. Okay, that was a simple example of one cycle of the Kalman filter. In the prediction, we use the motion model, and in the update, the measurement and measurement model are used to update the state density.